nameless gentleman once built a machine and disappeared into the thin air to travel through time. When he landed in the distant future, he found that humanity has devolved into two remaining groups: the fragile childlike Eli, who descended from the generations of comfort and dependence; the second group, the ape like Morlocks, who live underground in tunnels and operate the remaining machinery filled chambers. Hoping the future might improve, the time traveler ventured even farther. He saw weird crab like creatures crawling on the empty shores, and finally a cold, silent, lifeless earth orbiting a dying red sun. This story is from a famous science fiction novel, The Time Machine by A.G. Wells. A.G. Wells was deeply inspired by thermodynamics while writing this book. But why does this story, and reality for that matter, will always move forward? Who is restricting a broken teacup from unbreaking? The laws of physics? No. All the laws of physics are time reversible. It's actually due to statistics and probability. Let's flip 4 coins simultaneously. These are all the possible combinations of head and tail that you can get. The probability of getting any one of these combinations is 1 by 16. That is, your chance of getting all the heads or all the tails, or tail, head, head, tail, is the same. But if we group them into these possibilities of just the number of heads and tails like this without the order, and I ask you, what will you bet your life on? All the heads? Or 2 heads, 2 tails? Of course 2 head, 2 tails. That's more sensible. Simply because there are 6 different ways this particular state is achievable. This does not mean that all the heads will never come up. There is just one way to achieve it. Now, take a box of 6 gas molecules. There's actually only 4 ways to stack them all in a corner, but many different ways for them to spread out. So, it's just more likely they will. In reality, the number of gas molecules is in the order of 10 to the power 23. So, the probability of all of them going to one corner from being spread out is unimaginably tiny. You'd have to wait longer than the lifetime of the universe to see it once. Now, the different ways a system can arrange itself have a nerdy name: microstates. So the system naturally evolved towards a state that has more microstates. Now, if you take the logarithm of the number of microstates and multiply it by a constant, you get what physicists called entropy. And that's the famous law: the total entropy of the universe cannot decrease. But entropy isn't just about how many ways you can arrange particles. It's also about how the system's energy is distributed. When energy is concentrated, say a few particles hold most of it, there are only few possible configurations. That's low entropy. But if the same energy is shared across a large number of particles, there are countless ways to arrange it. That's high entropy. And over time, the system naturally shifts towards the state with the most possible arrangements, where the energy is spread out, and most particles have roughly the same amount of energy. That amount is usually very low, but it's equalized. And that's where our universe is headed. The sun is a highly concentrated source of energy, that is low entropy source. That energy radiates outward and reaches Earth, where it hits the ocean, the land, the atmosphere unevenly, depending on Earth's position. All the natural processes we see, winds blowing, rivers flowing, storms forming, happen because of these uneven distribution of energy. In other words, everything is working to spread out the sun's concentrated energy. Living things, plants, animals, even us, do an incredible amount of work every day. Growing, healing, thinking. But life at its core is highly ordered. Cells, organs, brains are all organized, structured systems. And to maintain that order, life needs a constant input of concentrated energy from outside. For us, that's mostly the sun. We absorb it, use it, and then release it back into the environment, but in a more spread out, disordered form. This redistribution of energy increases a lot if intelligent life is involved. Just look at all the things that we have built and things we destroyed. All of that required concentrated source of energy. And once we did all the work, all is left is very dispersed energy. But what's the problem with dispersed energy? Well, it's uniform everywhere. We need a gradient, a difference in energy to get work done. So, the uniformly dissipated energy is completely useless. And intelligent life increases entropy just by learning and processing information because you need energy to learn things. And turns out, erasing the acquired information isn't free either. In 1961, Rolf Landauer realized that erasing one bit of information increases the entropy of the environment. Now computers encode and erase a lot of information every day. Just think all of the brain rots. Training modern AI models, especially the large ones, demands enormous power, hundreds of megawatt hours of electricity, and generates heat. To cool down the data centers that run them, huge amounts of water are needed. But there is no reason for you to think that we single-handedly are increasing all the entropies of the universe. There are billions and trillions of galaxies, all the stars are burning and distributing energy every day. But even then, the amount of increase in entropy is really small if you compare it to the black holes. Yes, black holes are the biggest storehouses of entropy in the universe. In fact, the entropy of a black hole is proportional to the surface area of its event horizon. The bigger the black hole, more is the entropy. Just one supermassive black hole can contain more entropy than all the stars and gas in the galaxy combined. So, where is all of this heading? For us, a lifeless Earth under the dim red sun. And for universe, as time goes on, the stars will burn out one by one. The universe will grow colder and darker. White dwarfs, neutron stars, and black holes will be all that remain. Even they won't last forever. Over unimaginably long time scales, black holes will evaporate through the Hawking's radiation. All ordinary matter composed of protons would decompose. At that point, entropy will have reached its maximum, leaving behind a cold, non-interacting uniform soup of elementary particles and faint low-energy photons. Energy everywhere, but not useful enough to cause anything interesting anymore. And that's your journey through the time machine.